So, in 2026, the AI model that aced the bar exam, passed medical boards, and wrote flawless Python code.
He was just fired from its first corporate job.
Exactly. It's wild. It was literally fired.
Yeah, I mean, it is really the ultimate reality check for the entire technology industry right now. We've spent years just watching these models perform these incredible intellectual gymnastics, right?
Yeah.
In these pristine laboratory conditions.
Right. Isolated environments.
Right. And we just sort of assumed that meant they were ready to run our actual businesses.
Which, spoiler alert, they aren't. And welcome to today's deep dive, everyone. We are pulling back the curtain on this widening and frankly startling gap between theoretical AI capabilities and physical real-world reality.
It's a huge gap.
It really is. And we have a massive stack of sources today. We're looking at everything from 2026 AI benchmark reports to academic papers on heterogeneous computing, all the way over to macro energy infrastructure analyses.
Yeah, the energy piece is fascinating.
We're definitely getting into that. Because our mission today is to figure out exactly why the AI models that look like absolute geniuses on paper are failing in deployment.
Right.
And on top of that, how the sheer physical energy required to run these autonomous agents is forcing tech giants to literally rewrite the rules of the global power grid.
Yeah, we're witnessing the exact moment the digital realm violently collides with the physical realm. I mean, for decades, the cloud has always felt weightless, right? Like this invisible, frictionless space where code just runs.
Or magic.
Exactly. But the ultimate bottleneck for the future of artificial intelligence, it isn't a lack of training data or better code. It is the hard physical laws of thermodynamics.
Okay, let's unpack this. Because if you just casually read the press releases right now, everything sounds flawless.
Sure, the marketing is incredible.
Yeah. Every new frontier model that drops claims to be the most intelligent system ever built. And they back it up with these absolutely staggering benchmark scores.
But our sources are telling a very different story about the actual mechanics of those tests.
Yeah, so let's talk about that. Let's start with the benchmarks.
Well, for years, the gold standard for measuring an AI's general intelligence was a benchmark called MMLU.
That's the massive multitask language understanding test, right?
That's the one. It evaluates 57 distinct academic subjects. And, just a few years ago, models were scoring around like 35%.
Which is basically guessing.
Right. But today, every single frontier model scores above 88% on it.
Which, I mean, on the surface, that sounds phenomenal to anyone listening, right? 88% is a solid B+ across 57 different subjects.
It sounds great, but when you look closely at the data, that test is functionally saturated.
Meaning it's maxed out.
Exactly. When every major model clusters around 88 to 90%, the test stops actually measuring intelligence. The differences between the models at the very top have just become statistical noise.
Which brings us to this really fascinating foundational concept from economics that our sources highlight. Goodhart's law.
Goodhart's law, right.
Yeah. It states that when a measure becomes a target, it ceases to be a good measure.
Right, because people just game the system.
Exactly. AI labs are no longer just trying to build broadly capable smart models. They are dedicating massive engineering resources specifically to beat these exact evaluation tests.
Yeah, and the industry actually coined a term for this. They call it benchmaxing.
Benchmaxing, I love that term.
It's very descriptive. Labs are just squeezing every fraction of a point out of these tests. They might tweak the temperature settings of the model just for that specific evaluation, or they heavily weigh their training data toward content that's highly adjacent to the benchmark questions.
Just to juice the score.
Right. But the most alarming mechanism here, the real problem, is data contamination.
Yes. Data contamination is basically the quiet crisis of AI testing right now.
Oh, absolutely. And to understand it, look at the SWB bench example in our sources.
Okay, yeah, let's break that down.
So SW Bench Verified was the absolute gold standard for testing an AI's autonomous coding ability. It used 500 human-validated GitHub issues from real, widely used Python repositories.
So real-world problems.
Real problems. To pass it, the AI had to navigate thousands of lines of code, locate the specific bug, and write a functional patch.
And the models were absolutely crushing it, right?
They were. But here's the catch. They weren't actually reasoning through a novel software engineering problem.
Because they'd already seen the answers.
Exactly. Because these models ingest basically the entire public internet during their training phase, right? So their web crawlers had already scraped those exact GitHub issues.
Complete with the human-written solutions.
Yep. So when the AI took the test, it wasn't acting like a brilliant programmer. It was acting like a student who got a copy of the final exam the night before.
He was just reciting a memorized string of code.
Exactly. It's just regurgitation.
And the contamination was so pervasive that OpenAI actually dropped the SWE benchmark entirely from their reporting.
Which is a huge admission.
It really is. And what happened next is incredibly telling. The industry shifted to a new evaluation called SWE Bench Pro.
Right, the pro version.
Yeah, and this version uses private, unseen code repositories that are locked behind enterprise firewalls.
So the models couldn't have possibly memorized them?
Zero chance. And when forced to actually reason through private, unseen code, the scores completely collapsed.
It was a bloodbath.
Models that look like senior software engineers dropped to roughly a 23% success rate.
23%. I mean, if we connect this to the bigger picture, it explains a massive discrepancy that's plaguing the enterprise world right now. Our sources document a 37% gap between how these models perform on lab benchmarks and how they actually execute when deployed into real corporate environments.
Wow. 37%. It's like a car company leading their 2026 safety pitch with a crash test that was designed in 2015.
That's a great analogy. Like, sure, every car on the market passes it with flying colors today, but a pristine, controlled crash into a padded wall, that tells you absolutely nothing about how that vehicle will handle a multi-car pileup on a rainy highway at 70 miles per hour.
Right, because benchmarks evaluate single-turn, closed-ended tasks. Real-world AI requires continuous, ambiguous processing.
It's messy out there.
It is. That continuous processing is the real hurdle. In a corporate environment, an AI agent has to interact with other software systems. It has to navigate incomplete data, handle vague instructions from human managers.
Which happens all the time.
Right, and it has to run for extended periods without hallucinating. The public tests simply do not measure the endurance required for real deployment.
Okay, so if you're listening to this and you're evaluating AI tools for your own company, public benchmarks are basically a mirage at this point.
Pretty much.
So how do you actually know if a model is going to work for your specific, messy, real-world workflows? Well, the consensus across all our sources is entirely unified on this front. The only benchmark that matters is your own proprietary data.
Your own stuff.
Yes. You have to abandon the generic leaderboards entirely. The recommended protocol is to isolate, say, 10 to 20 highly representative tasks.
Like actual customer service prompts or your complex internal financial documents.
Exactly, or your proprietary code.
Yeah.
And you run the models directly against those specific workflows.
But wait, the mechanics of evaluating that seem completely unscalable. Like, you can't just have a human manager sit there and manually read tens of thousands of AI-generated responses to see if the model successfully analyzed a financial quarterly report.
You absolutely cannot. It would take years,
Huh.
which is why production-ready AI evaluation has adopted what they call a layered approach.
Okay, how does that work?
The first layer is entirely automated metrics. You deploy unit tests and statistical evaluations just to catch obvious formatting failures or syntax errors.
So just filtering out the junk.
Right. It's incredibly cheap, it scales infinitely, and it filters out the lowest hanging fruit.
Got it. Then what?
Then you move to the second layer, which is essentially using AI to grade AI. It's called the LLM as a judge framework.
Oh, right. So you take a massive, powerful frontier model and you use it to rapidly screen the outputs of your smaller deployed model.
Exactly. The LLM as a judge is highly effective for flagging factual deviations or logical inconsistencies at scale, but it has a hard ceiling.
Because it's still just an AI.
Right. An AI judge cannot guarantee ground truth correctness for highly complex, domain-specific edge cases. Which brings us to the final and, most expensive layer of evaluation.
Human expert review.
Yep, human experts.
Our sources specifically point to platforms like Keeley Technology and OpenAI's GDPval utilizing verified domain specialists.
Not just gig workers.
No, we are talking about practicing corporate attorneys, mathematicians, and physicians with 14-plus years of clinical experience, basically acting as the final arbiters of AI quality.
Right.
But wait, I have to push back here.
Go for it.
We are spending billions of dollars to build highly advanced, supposedly autonomous cognitive machines.
Yeah.
But the ultimate safeguard for their deployment is an expensive human being. Doesn't that completely defeat the economic purpose of the technology?
I mean, it seems entirely counterintuitive until you examine the mechanics of professional risk.
Professional risk.
Yeah. Think about high-stakes environments, regulated industries, clinical healthcare, enterprise finance. In those fields, correctness isn't merely about outputting a fact.
Right, the stakes are way higher.
A hallucinated legal citation or a misread medical scan carries catastrophic liability. Professional correctness requires judgment, nuance, and an understanding of regulatory compliance that machines just cannot verify on their own yet.
So when the cost of a failure is severe, automated evaluation is fundamentally insufficient.
Exactly. You have to anchor the system to human ground truth.
Okay, so let's trace the causality here, because this is where the story gets crazy. Human evaluation is incredibly expensive and slow.
It's very slow.
So to get around that bottleneck, businesses deploy autonomous AI agents. Instead of a human checking the work, the AI agent is instructed to research a topic, draft a report, critique its own draft, revise it, and check it again.
A continuous loop.
Right. You've removed the human from the loop, which feels like a massive success. But that continuous autonomous looping triggers an entirely new crisis.
Yes, a crisis of physical infrastructure.
Well, let's talk about the energy.
To understand the sheer scale of this, we have to look at the architectural shift from training AI to running AI, what the industry calls inference.
Inference, right.
For a long time, the dominant narrative was about the massive power required to train a new model. But training is a burst workload.
Meaning it has an end date.
Exactly. You run the supercomputer. But inference is continuous. And inference now accounts for 80 to 90% of the total AI compute load across major vendors.
80 to 90%.
Because we aren't just sending a single prompt to a chatbot anymore, right? Autonomous agents are looping 24/7. They're constantly pulling data from memory, running reasoning pathways, communicating with other software agents, and just taxing the memory bandwidth of the hardware nonstop.
And the hardware evolution required to support that continuous looping is staggering. Like, a few years ago, a standard enterprise data center rack drew roughly 10 to 15 kilowatts of power.
Which was a lot back then.
Right. And then the previous generation of AI chips pushed that boundary to 35 to 45 kilowatts per rack. But the new NVIDIA Blackwell GB200 racks that are detailed in our sources,
Oh, the Blackwells.
they draw an eye-watering 120 to 140 kilowatts per single rack.
It's hard to even conceptualize that much power in that small of a space.
At 140 kilowatts,
Mm.
you're generating so much thermal density that traditional air conditioning is physically useless. Like, you can't blow cold air fast enough to stop the silicon from melting.
Right, which is why our sources point out that direct-to-chip liquid cooling is now an absolute mandatory requirement.
Liquid cool.
Yeah, we are pumping chilled liquid directly over the processor plates just to keep the infrastructure from bursting into flames.
That is insane. And it creates this fascinating macroeconomic paradox. Do these autonomous agents help or hinder total energy efficiency?
Well, at the macro level, they severely hinder the raw power grid by drastically increasing the baseline continuous demand.
Just sucking up gigawatts.
Exactly. But at the micro level, if orchestrated correctly, agents can execute complex tasks far more efficiently than a human utilizing traditional software.
Which means the old ways of measuring data center efficiency are completely dead.
Oh, entirely dead.
Like, for over a decade, the industry obsessed over PUE power usage effectiveness. A PUE of 1.0 meant you were perfectly delivering power to your servers without wasting a single watt on overhead, like cooling or lighting.
Right. But a data center with a perfect PUE that is running terribly inefficient looping agent workflows is just wasting gigawatts of energy perfectly.
Wasting it perfectly, wow.
Yeah, PUE tells you absolutely nothing about the actual cognitive output of the silicon.
So what does this all mean for the industry? Our sources say they've rapidly shifted to a new primary performance metric: tokens per watt, or intelligence per watt, IPW.
IPW is the new gold standard.
We are no longer just looking at the power draw of the building. We are measuring exactly how much actual thinking we extract from every single drop of electricity.
Precisely.
But wait, if we establish tokens per watt as the new ultimate metric, are we just setting up another Goodhart's Law scenario? Won't hardware companies just start benchmarking their chips to spit out low-quality tokens as fast as possible to artificially inflate their IPW score?
That is the exact risk. Which is why achieving a genuine high intelligence per watt score requires a fundamental redesign of how we run hardware, not just a change in how we measure it.
A redesign at the silicon level.
Yes. One of our academic sources outlines a highly advanced framework called QIL, quantifying edge intelligence via inference time scaling laws.
That's a mouthful.
It is, but the core mechanism behind QIL is actually pretty straightforward. It's called heterogeneous computing.
Heterogeneous computing, meaning different types of processors working together.
Exactly. Instead of throwing every single AI task at a massive, incredibly power-hungry GPU, you break the agent's thought process into distinct microtasks, and you route them dynamically based on hardware efficiency.
I love this concept. Think of it like a massive commercial kitchen, right?
Okay, yeah.
Your GPU is the Michelin star head chef. You do not want your head chef spending 3 hours just chopping onions. That's a massive waste of expensive resources.
Exactly. So in this analogy, the CPU is the maitre d', organizing the incoming requests.
Right.
The GPU does the heavy cognitive lifting, the complex reasoning. And the bandwidth-heavy repetitive tasks like token decoding are routed to a highly specialized low-power neural processing unit, or NPU.
The NPU is your prep cook.
The NPU is the prep cook. By dynamically routing tasks at the silicon level like this, the QEIL framework doesn't just bump efficiency by a few percentage points.
No, the numbers are huge.
Our sources show it reduced average power consumption by 68% and improved the intelligence per watt by over 5 times across multiple frontier models.
A 5x improvement is incredible. But here is the terrifying reality. Even if we achieve a 5x improvement in intelligence per watt through heterogeneous computing, the macro demand for autonomous agents is scaling so violently that it completely swallows those efficiency gains.
Yeah, Jevons paradox in action. We make it more efficient, so we just use way more of it.
Exactly. We are no longer talking about standard 20-megawatt data centers. Tech giants are currently building massive AI campuses that require 100 to 750 megawatts of continuous power.
750 megawatts. To contextualize that scale for you listening, a single 500 megawatt facility consumes approximately the same amount of electricity in a year as 360,000 residential homes.
One facility, 360,000 homes.
Yes.
Now, for years, the major tech firms proudly committed to running purely on renewable energy like wind and solar.
Right.
That was the big PR push.
Yeah, the climate pledges.
But at a 750 megawatt scale, that promise has just slammed into the harsh reality of grid inertia and intermittency.
It's purely an issue of physics. The power grid requires absolute stability. Solar and wind are highly intermittent. They typically generate power only 20 to 35% of the time, depending on weather and daylight.
The sun goes down, the wind stops blowing.
Right. But continuous inference cannot tolerate intermittency. If a data center experiences even a microsecond voltage drop, complex looping AI operations can crash entirely.
The agents just die mid-thought.
Exactly. AI campuses require massive, unrelenting baseload power. That's electricity that flows at maximum capacity 24 hours a day, 7 days a week.
Now, you might be thinking, well, just store the excess solar power in giant batteries during the day, but the math in our sources is absolutely brutal.
It really is.
To physically store enough lithium-ion backup power for a 5-gigawatt AI cluster, that would cost over $5 billion just for the batteries.
And the physical footprint of those batteries would be astronomical. It is physically and economically unfeasible.
Which leaves only a handful of options for carbon-free baseload power at a gigawatt scale. Hydroelectric infrastructure is largely tapped out globally.
We've built all the dams we can build.
Right. Natural gas is incredibly reliable and fast to build, but it produces heavy carbon emissions, which violates all those corporate climate pledges.
So the technology sector has pivoted aggressively toward the only remaining viable source.
The nuclear renaissance.
Yeah.
I mean, in an absolute twist of fate, software companies are literally restarting dormant nuclear reactors just to feed the physical demands of their AI models.
Right. Let's actually look at the specifics of these 2026 infrastructure deals because they are staggering. Microsoft signed a historic 20-year, $16 billion power purchase agreement with Constellation Energy.
$16 billion. Wow.
And their explicit objective is to completely refurbish and restart Unit 1 of the 3 Mile Island nuclear plant in Pennsylvania by 2028.
3 Mile Island.
Yes. And Microsoft is purchasing 100% of its generated output exclusively for Hill data centers.
That's wild. And Amazon has taken a similar route. They invested over $20 billion into a colossal data center campus located directly adjacent to the Susquehanna nuclear plant.
Just plugging right into the reactor.
Literally. And Google is pursuing a slightly different strategy. They're signing deals with Kairos Power to deploy a fleet of next-generation small modular reactors, or SMRs.
Right, which are designed to be constructed much faster than traditional massive cooling tower plants.
But Meta's procurement strategy, that truly illustrates the scale of this pivot.
Oh, Meta's going all in. In a single month, Meta locked in agreements with Vistra, TerraPower, and Oklo.
And Oklo notably counts Sam Altman as a major backer, right?
Yes, exactly. And those Meta deals secure over 6 gigawatts of nuclear power by 2035.
Here's where it gets really interesting. The business model of the technology industry has completely inverted.
How so?
Well, a decade ago, commercial nuclear power in the United States was viewed as a decaying industry. It was too expensive to maintain, hampered by red tape, completely lacking public support.
People were shutting plants down.
Exactly. But today, the most aggressive, well-funded buyers of nuclear energy on the planet are software companies.
They are essentially forced to become energy utilities. Think about it. They are locking up the entire output of nuclear reactors decades before they even come online.
Decades in advance.
Because power procurement is no longer just a localized facilities management issue. It is a board-level competitive moat. If you cannot physically secure the gigawatts, you cannot run the autonomous agents.
The AI revolution has basically transitioned from a software engineering challenge into the heaviest industrial infrastructure challenge of the 21st century.
Without a doubt.
Wow. Let's take a moment to just recap the journey we've navigated today. We started by dismantling the illusion of public benchmarks, detailing how data contamination and benchmarking render a 90% test score almost meaningless for real-world deployment.
Right, the SWE bench collapse.
Yep. Then we explored the mechanical necessity of testing AI on your own specific data and why the nuance of high-stakes decisions requires human experts to establish ground truth.
And from there, we traced how the shift toward autonomous looping agents triggered a massive surge in continuous inference compute.
Right, the 140 kilowatt liquid-cooled server racks, the death of PUE.
And the critical shift toward tokens per watt, driven by heterogeneous computing frameworks like QEIL.
Head chef, prep cook. And finally, we witnessed how that insatiable physical demand for continuous baseload power has forced the world's largest tech companies to become massive investors in gigawatt-scale nuclear infrastructure.
If there is one critical takeaway for you listening today, whether you are integrating an AI tool into your small business workflow or just monitoring the macroeconomic shifts of the tech sector, it is this. The fundamental rules of the technology industry have changed.
They really have.
We are no longer operating in a purely digital sandbox.
Absolutely. Which brings me to a final thought I want to leave you with today. For the last 50 years, the technology industry has built its empire in the digital realm, writing code that lived in the cloud, invisible, weightless, and instantly scalable.
The frictionless era.
Right. But as artificial intelligence graduates from just an assistive chat tool to an autonomous system capable of continuous execution, it is forcing tech to conquer the physical world.
Yeah.
If the ultimate bottleneck for the future of artificial intelligence isn't silicon or software, but the physical laws of thermodynamics and the capacity of the electric grid, what happens when tech giants start redesigning our physical global energy infrastructure with the exact same aggressive velocity they use to redesign the internet?
That is the multi-trillion-dollar question.
It really is. Thank you for joining us on today's Deep Dive. We'll see you next time.